Hello, everyone, and welcome to Lecture 26 of Computer Architecture. Today, we're going to look at how to apply pipelining to the data path that we constructed in previous lectures. So let's reviewing what we did last time, which was we started talking about pipelining abstractly without kind of looking at the specifics of the data path. We actually didn't finish, so we will finish talking about that, and then I'll move on to talking about pipelining the data path. So last we used doing the laundry by 4 different roommates as an example to show what pipelining is and how it's useful. So in the example up here, every roommate did their laundry. It took them 2 hours, and then the next roommate started when the previous roommate finished. And we saw how this is inefficient and how the fourth roommate had to stay all the way up to 2 a.m. to do their laundry. And we saw how we can improve on this by pipelining, which is as soon as the first roommate is done with the washing machine, the second roommate can start using the washing machine without waiting for the first roommate to finish all their laundry steps. And the same thing goes on until we get better. They all finish before 9:30 a.m. And we said that when we do pipelining, when we take a task and we pipeline it to S stages, if all the stages are balanced and if we have a very large number of tasks, we get a speed up of around S, where S is the number of stages. We then looked at pipelining the data path, and we said that when we pipeline the data path, the MIPS in the MIPS pipeline, we divide it into 5 stages: instruction fetch, instruction decode, execute, memory, and writeback. And we saw that the stages are not the stages of the MIPS data path are not balanced. Some stages take longer than others. So the speed up of the data path is not going pipelining is not going to be 5x. It was actually 4x. So here we saw how without pipelining, every instruction took 800 picoseconds. So 3 instructions took 2,400 picoseconds. But then with pipelining, because we're applying pipelining, now all the stages need to be as long as the longest stage, because we're going to do a stage every cycle. So the cycle needs to be long enough to fit the longest stage. Consequently, what happens is that the instruction decode stage where we read the register and the writeback stage where we write the registers, even though those took 100 picoseconds without pipelining, with pipelining we're going to give them 200 picoseconds because we need to give the other stages 200 picoseconds because that's how long the other stages take. And we saw that because we don't have the stages are not balanced, we don't have a 5x speed up from having 5 stages. We actually have a 4x speed up, and the 4x comes from the time it took to execute a whole instruction over the time that it takes to execute one stage. Because as n grows large, the tail stages, the remaining stages of the last instruction become negligible. So every instruction effectively takes as long as its first stage, and then you have the total instruction duration over without pipelining over the duration of a stage with pipelining. That will be your speed up when the number of instructions is very large. We then looked at we saw that pipelining is a very powerful optimization, but we said that there's a catch, and the catch is hazards. So when we do pipelining, when we start overlapping the execution of different instructions and using the same hardware, what happens is we run into these situations called hazards, which is where an instruction cannot execute because it depends on some other instruction or it conflicts with some other instruction for something. And there are 3 types of hazards: data hazards, where an instruction depends on another instruction's data. Structure hazard is where 2 instructions are using the same hardware structure. And control hazards are where we don't know what is the next instruction we need to fetch because that depends on an instruction that is still executing. So first, we saw data hazards, and we said that in this example over here, the add instruction writes S0 to the register file in the cycle 5 after the 800 picoseconds. However, the subtract instruction needs to read S0 from register file in cycle 2. So obviously we cannot when sub tries to read S0, it's not going to have the right value because the right value is not written until cycle 5. So one solution for this was to stall. So to stall the subtract instruction until the reading happens from the register file happens after the writing to the register file. Another optimization we did is we modified the way we read and write from the register file so that we can write in the first half of the cycle and read in the second half of the cycle. So the write actually takes place in the middle of the cycle as opposed to the end of the cycle. And by doing this, we were able to do the instruction decode at the same cycle as the write back instead of doing it after the write back. And then saw another powerful optimization, which is forwarding or bypassing, where we observed that even though S0 is not written until the write back stage, it's actually available after the execute stage. And here in the sub instruction, even though S0 is read during the decode stage, it's actually not needed until the beginning of the execute stage. So what we can do is we can actually sneak the output of the ALU back to the input of the ALU in order for us to avoid having to stall entirely. Now, this was possible when we had an add instruction followed by a subtract instruction, but it was not possible for load instructions because the value of, if this was a load instruction here and that was we were loading S0 from somewhere, the value of S0 is not available until after the memory stage. So in this case, we can't forward because you can't forward back in time. So what we had to do in this stage is it was inevitable for us to stall at least for one cycle until we were able to forward from the output of the memory stage to the input of the execute state. So this is how we dealt with load use data hazards. But we said that can actually do instruction scheduling where it takes any code where you have a load followed immediately by a use of the value that was loaded, and it reorders instructions as long as it's legal to make sure that there is at least one instruction between a load and its use. And this way we can avoid having to stall in the pipeline because we don't like to stall. Stalling hurts performance. We like to avoid it as much as possible. We then looked and we said that the MIPS pipeline does not have structure hazards because we're using separate memories for instruction and data, and also because we're using our register file allows us to read and write on the same cycle. However, hypothetically, if MIPS did not use different memories for instructions and data, then we could have a structure hazard between the memory stage and the instruction fetch stage. So for example, here, if load word was loading from memory and we were using the same memory to load instructions, then we wouldn't be able to fetch the add instruction over here and we'd have to wait for the next stage. Similarly, if the MIPS pipeline did not allow to read and write to the register file on the same cycle, then here this write back stage would conflict with this instruction decode stage. We wouldn't be able to write to the register file and read from the register file on the same cycle, so we'd have to stall the add instruction until we can read. And in fact, even in this case, this instruction is also writing back, so we'd actually have to keep stalling until we get to a cycle where no instruction is writing back. Okay, so this was a quick overview of what we covered last time. Any questions about what we covered last time before I move on to today's material? Okay, so what I'll do today is I'll continue talking about control hazards, which we're not able to finish last time. And then after that, we'll move on to talking about how to apply pipelining to the data path that we had built before. So recall what control hazards occur when we cannot decide what instruction to fetch. And the reason is that the next what instruction to fetch depends on the outcome of another executing instruction. For example, branches, right? So when you have a branch takes a while to execute, right? You need to fetch the branch instruction, and then you need to decode it, then you need to get the registers, you need to compare them, you need to calculate the target address of branch. All of that takes time. So fetching the next instruction depends on the branch instruction, and so we cannot proceed before resolving the branch. So what the pipeline does, in order to avoid stalling as much as possible because of branches, so like we said, we need to compare the registers and compute the target as early as possible in the pipeline to minimize how much we stall because of branches. So what the MIPS pipeline does is that rather than using the ALU to do the comparison, what it actually does is that it will do the comparison in the instruction decode stage, and resolve the target address in the instruction decode stage. Okay, and what this does is that it allows us to resolve the branch by the end of the instruction decode stage to minimize how much we stall. So this is what the MIPS pipeline does. So without pipelining, we just used the ALU to do the comparison because we already had a way to do it in the ALU. But with pipelining, if we wanted to use the ALU to do the comparison, this was going to delay resolving the branch for too long, and this is why we would add a custom comparator to the data path. Okay, so we will look at this later, but for now, what I want you to know is that the result of the branch will be resolved after the instruction decode stage. Okay. Now let's see how control hazards. So let's say I have this code over here. I have an add instruction, and then I have a branch instruction. Okay, so with the branch instruction, I fetch the branch. So now I need to decode the branch. So decode the branch is going to happen here, but in the third cycle. Now the problem is that I cannot do the instruction fetch for the next instruction. Why not? Because I don't know the next instruction. I don't know the next instruction until the end of the decode stage when the branch is resolved. Okay, so what do I need to do in this case? Right, exactly. I need to stall. I can't fetch the next instruction because I don't know what it is. So I'm going to stall, right? I cannot fetch the instruction because the branch outcome is unknown yet. So I'm going to stall until the end of the instruction fetch stage, the instruction decode stage. And now by the end of the instruction decode stage, now I know the result of the branch. Now I can go ahead and fetch the next instruction. Okay. So every time I have a branch, I'm going to need to have a stall before I can fetch the next instruction. Clear? Okay, well this is we don't like stalls, right? We always tried to find a way to avoid stalls. With data hazards, we did forwarding. With the load use hazard, we let the compiler do instruction scheduling. With structure hazards, we kind of had separate structures for doing different things. All of that just to avoid having to do stalls. Okay, so we would like to do the same thing with branches. We'd like to avoid doing the stall, but the problem is that there's no way for us to find out the result of the branch after instruction fetch, right? There's no way for me to figure out the result of the branch after instruction fetch. I don't even know that it's a branch. Okay, so what can we do? What can we possibly do to avoid stalling here? Yeah, what can we possibly do to avoid stalling? Know if it's a branch. Okay. Even if we know the branch, we still need to know if they're the result, if the registers are equal. We need to know the target address, all of that. Right. So what we can do is we can try to predict the branch. So processors actually have a very important optimization called branch prediction. So the idea is that even in the MIPS pipeline, we only pay one stall for the branch. But in many cases, in compute and processors, pipelines are much longer than 5 stages. You can have 10 stages, even 15 stages in pipelines. And usually the branch takes many cycles to get resolved. So here, the penalty from stalling all of these cycles because of the branch is very high, and it's not acceptable. So what processors do is they actually employ something called branch prediction. So what branch prediction is it's a technique to predict the outcome of a branch. Okay. So what the processor will do is when it fetches the branch and sees that it's a branch, what it's going to do is rather than waiting until the branch outcome gets resolved, it's just going to predict what the outcome of the branch is going to be, and it's going to start executing. So either it predicts that the branch is not taken and continues executing the next instruction, or it predicts that the branch is taken and continues executing the instructions that are the target of the branch. Okay, so in most cases, we can actually predict correctly. So in most cases, the processor can actually predict correctly, but in case it predicted incorrectly, then what the processor will do is that it will replace the instructions that it started to execute. It realizes, oh, I should not have executed these instructions, so it will kind of flush those out of the pipeline and replace them with stalls. Okay? So this way, if we predict correctly, it's like we did not have any stalls. And then if we predicted incorrectly, which is less often, that is only when we pay the penalty of stalling. Okay. Now in MIPS pipeline that we will cover in class, what we're gonna do is we're gonna predict that branches are always not taken. So we'll always predict that the branch is not taken. So that way, if the branch is not taken, we will not pay any stall penalty. But if the branch is taken and we predict incorrectly, that is when we will pay the stall penalty. Okay, now this is not the best form of branch prediction. There are better forms of branch prediction, and I will talk about those very shortly. But this is what we're going to do in this class. We're always going to predict that a branch is not taken, and if it ends up getting taken, we're going to replace the instruction that we executed with a bubble. Okay, so let's take a look. So here, in this example over here, we have a branch instruction. Okay, so what we'll do is we're going to fetch the branch, and the branch is not going to get resolved until 600 picoseconds, until the end of the third cycle. But what we will do is, rather than waiting for the branch to get resolved, we're going to predict that the branch is not taken and execute the next instruction after the branch. Okay, so here we're just going to start fetching the next instruction after the branch. Now, at the end of the third cycle, if we find out that the branch is not taken, so if our prediction is correct, that means it was correct to fetch the instruction after the branch. So we just continue executing the instruction after the branch, and we don't pay for any stalls. However, if our prediction was incorrect, so if at the end of the third stage we find out that our prediction was incorrect, what we will do is this load instruction that we fetched, we're not going to execute it. So it's as if we stalled. It's as if we had a bubble here in the third cycle. And on the fourth cycle, we will proceed to fetch the result of the branch, because by now, at the end of the third cycle, we know for a fact what the branch target is. So we go on to execute the instruction that's at the target of the branch. Okay? So someone's asking if the third instruction starts at 200 picoseconds. No, the third instruction is starting at 400 picoseconds. This 200 picoseconds here indicates that the distance between this instruction fetch and this instruction fetch is 200 picoseconds because we don't stall. However, if we had to stall, then the distance will be 400 picoseconds, which is 2 cycles. Okay. So yeah, the third instruction fetch up here starts at 400 picoseconds, not 200. 200 here refers to the distance between the beginning of this instruction fetch and the beginning of this instruction fetch. Any other questions? Is this clear to everyone? What happens when we predict correctly? What happens when we predict incorrectly? So here we're only going to pay the stall if we predict incorrectly. It turns out that in processors, we're actually a processor can actually predict branches with very high accuracy.
Sir,
Yes.
If we predict incorrectly, we would have done a whole instruction set, fetching and everything in vain, right?
That's true. So if we predict incorrectly, the instruction that we fetched over here, we're just not going to use the instruction that we fetched. So we'd have fetched it unnecessarily. Okay, so we would have done unnecessary work. But the idea is that we'd rather do work unnecessarily than pay for the stall. That way we can make our processor as fast as possible.
But here, there is a big stall actually. All of these bubbles.
Yeah, but we only pay 1 cycle for this, right? The bubbles in the pipeline, but the what you feel is just 1 cycle, right? Because here between the end of this and the end of this is just 1 cycle, right?
Oh, right. Okay, thanks.
Yeah. And if you didn't do branch prediction, you would have had to pay for the stall every time. But because of branch prediction, you only pay for it when you mispredict. Okay, other questions? Okay, so it turns out that in reality, we don't just always predict branches as taken. There's different kinds of branch predictors. One kind of branch prediction is static branch prediction, and static branch prediction just predicts a branch based on its behavior. So, for example, an example of static prediction is we always predict forward branches as not taken, and we always predict backward branches as taken. Now, why is this useful heuristic? Well, where do forward branches come from? Forward branches come from if statements, right? So we have if else. So a forward branch will branch to the else, or or if there's no else, a forward branch will branch after the if statement. Now, a lot of because of the way programmers write programs, a lot of times when you have an if statement, a lot of times the condition of the if statement is true. So by predicting a forward branch as not taken, it's like saying that I'm going to assume that the condition is true, and I know that in most of the cases conditions are true, because programs, when they write conditions, they write them in their true form, not in their false form. Okay, and then the other case is for loops. So if I have a while loop, the branch is going to, if the branch is taken, that means we're going to branch outside of the loop. If the branch is not taken, that means we're going to go into the loop, right? So with loops, I'm not going to take the branch, when I'm going to go into the loop most of the time, right? So if I could have a loop with 1,000 iterations, I go into the loop 1,000 times, and then I branch out of the loop once. So that is why if I have a forward branch, then predicting it not taken means I will predict correctly for every iteration of the loop except for the last iteration. Okay, so I will predict correctly for every iteration of the loop except for the last iteration. For backward branches, where do backward branches come from? Well, they come from do-while loops. I have a backward branch whenever I have a do-while loop. So for a backward branch, that means I'm branching back to the beginning of the loop. So in this case, if I'm branching back to the beginning of the loop, then I want to branch. I branch back. I take the branch every iteration, and only on the last iteration I will not take the branch and go after the loop. So that is why if it's a backward branch, I can guess that this is a do-while loop, and I will predict it taken every time. So this is the intuition behind static branch prediction. We also have dynamic prediction, and dynamic branch prediction is even fancier. And this is actually what many processors use, and it's very accurate. What dynamic branch prediction does is that it measures the historical behavior of the branch and makes a prediction based on the historical behavior. So it does it's like, well, the last time, or the last 2 times, or the last however many times I predicted this branch, I took this branch, so most likely I will also take it this time. Okay, so it records the history of how the branch behaved, and what it does is, based on this history, it decides what to do in the future. And if it predicted incorrectly, then what it does is that it updates itself, so that it updates its history, so that in the future it will predict correctly. Okay, is this clear to everyone? Any questions about control hazards and branch prediction? Okay, so if there are no questions, then we can move on to today's topic. And today we're going to talk about the data path. Okay, pipelining the data path. So the term MIPS pipeline, the MIPS ISA is designed for pipelining. The MIPS ISA is designed for pipeline. What do I mean by that? So when we pipeline, we want to divide these different aspects of the different parts of the data path into stages. And the MIPS ISA is designed in a way where these individual stages take a little amount of time. So for example, in MIPS, all instructions are 32 bits. What does that mean? That means that instruction fetch and instruction decode are easy and they can always be done in one cycle. Whereas in another ISA like x86, which has variable length instructions, some instructions could be 1 byte, some instructions could be 17 bytes. What does that mean? That means that instruction fetch is complicated because I need to fetch part of the instruction, check what it is, and then fetch the remaining part of the instruction. So instruction fetch is complicated, and so is instruction decode. So that makes it hard for us to divide them into stages that take one cycle. Another thing is that we have few and regular instruction formats. So this makes decoding and reading the registers in one step easy. Load and store addressing. So we can use the ALU to both calculate the address and do the arithmetic. So we can use the ALU as one stage for calculating the address and then accessing memory in the fourth stage. And then finally, because we access memory in an aligned way, memory accesses take one cycle. If we want to access memory in a way that was not aligned, it would actually be more expensive to access it, and we couldn't do it in one cycle. So these are the different ways that MIPS is designed to allow for easy pipelining. So with that, let's take a look at how we are going to pipeline this data path. So the data path, this is the data path that we constructed earlier. We have the instruction memory, register file, ALU, data memory, and here the multiplexer that controls writing back to the register file. And what we will do is we want to divide it. Remember, we said that we will divide the data path into 5 stages, and these stages are as follows. So this first part of the data path is going to be responsible for instruction fetch. The next part of the data path is going to be responsible for instruction decode. So here we're gonna take the instruction, break it into pieces, extract the registers we want to read and write to, right? Extract the offset, do a sign extension. We're also gonna have the controller. We're gonna do the execute. The execute stage is going to be one stage. So here we have our ALU, okay, and then we have the memory. So here we have the data memory that we read and write to. And then we have the write back stage where we select the value we want to write back and we write it back to the register file. Okay. Now, one thing to note here. So I told you before that the way we're going to deal with branches to minimize stalling on branches is we're going to resolve the branch in the instruction decode stage. Now, the data path that I'm going to show you today does not do that. And the pipeline data path that we're showing you today, we're going to resolve the branch over here in the execute stage and then finally in the memory stage. Okay, so we resolve the branch at the end of the execute stage, but later on we will look at how we're going to move this back to the instruction decode stage, so that we resolve the branch at the end of the instruction decode stage instead of resolving it at the end of the execute stage. Okay. All right, so how do we divide our data path into stages? Well, what do we want to do? What we want to do is we want to take, for example, an instruction and do the instruction fetch for the instruction. And then while the instruction that we fetched is doing the instruction decode, we want to start fetching another instruction. Now, can we just do this, right? Can I take the instruction that I read and start decoding it while I start fetching another instruction? Can I just do it the way the data path is now? I can't, right? I can't, because if I fetch an instruction, right, and then now I'm decoding the instruction, and if I fetch an instruction, excuse me, if I fetch an instruction and I come in and start decoding the instruction, and while I'm decoding the instruction, I start fetching another one, what's going to happen to the instruction over here? It's going to change, right? So what I need to do is, after fetching the instruction, I need a way to hold that instruction for the instruction decode stage so that it doesn't change while I am fetching the next instruction. Same thing between these two stages. When I read these registers and I want to use them in the execute stage, right? So I'm using the register values in the execute stage, but I'm going to start fetching new registers in the for the next instruction. So I don't want the new values that I fetch for these instructions to affect the values that are being used in the execute stage. So I need a way to hold the values in the for the execute stage while the instruction decode stage is fetching its own fetching new values. Okay, so how do I do this? And you're correct. What someone said in the chat is we're going to add registers. So what we're going to do is we're going to add these pipeline registers in between each of the stages. And what these registers do is they ensure that the input to each stage is held for the entire cycle and updated on the next cycle. So having this register over here ensures that we hold the instruction that we fetched. And in the meantime, we can fetch the next instruction without affecting the instruction that's being decoded. Here, we're going to, after we read these values on the next cycle, we're going to hold the values that we read from the register file while we read the registers for the next instruction without affecting the values for the registers in the execute stage. And same thing throughout the data path. Okay, so we have these pipeline registers that will make sure that we hold the values in between stages. And this is pretty much what we need to do for pipelining. We simply add these pipeline registers in between stages. Okay, and this is kind of the fundamental what we need to do for pipelining. Now we still have a few issues. Of course, we need to resolve hazards, right? So we need to deal with hazards, and we're going to look next time at how to modify this pipeline to deal with hazards. But we also have one small issue, and that small issue is now that we're not right. We're providing the wrong write register. Why is that? Well, when we want to write to the register file, we are writing to the register file in the writeback stage. So the value that we want to write to the register file belongs to the instruction that's going to be here in the writeback stage. However, over here, what we're doing is we're providing the number for the instruction that's being decoded. However, we only want to read the registers for the instruction that's in the instruction decode stage. We don't want to write the register for the instruction in the decode stage. We want to write the register for the instruction in the writeback stage. So what do we need to do to resolve this? How do we make sure that we are writing back to the correct correct register? Well, what we do is we're going to take for the instruction that's in the writeback stage, when we are decoding it, we're going to take its write value and we're going to take it with us. So here we're going to, rather than having the SMUX that's selecting either RS or RT, what we're going to do is we're going to take RS and RT with us. We're going to select between them over here, and then we're going to bring them all the way to the writeback stage. So now here I'm going to have the number for the register that I want to write to in the writeback stage. And then I'm going to take this value, and when I bring back the data that I want to write back, I'm also going to bring back the number of the register that I want to write back, and I am going to pass that as the write register. So this was one small fix that we need to do to make sure that we pipelined correctly. So we added the pipeline registers, and then of course we had to take the destination register with us from the decode stage all the way to the writeback stage, and then bring it back to make sure that we are writing back to the correct register. Okay, so now we have our pipeline data path. It was that easy. So does anybody have any questions about the pipeline data path? Okay, someone wants me to repeat the part about the writeback register. Okay, so when we write back to the register file, let me go back. When we write back to the register file, the instruction that is writing its result to the register file is not the instruction that is being decoded, right? An instruction gets fetched, then it reads its registers, and then it executes its value, it accesses memory if it needs to, and then it writes back. So the instruction that's going to write back to the register file is the instruction that is here in the write back stage. It's not the instruction that's in the decode stage. So the way things are right now is I'm passing the write register for the instruction that's in the decode stage. And that's incorrect. I only want to read the registers for the instruction that's in the decode stage. I want to write to the register for the instruction that's in the write back stage. Now, how do I know the register for the destination register for the instruction that's in the write back stage? Well, the way that I know that is by bringing it with me from the instruction decode stage. So that's why what we're going to do is we're going to take RS and R, select the destination register. We're going to bring the destination register number all the way with us to the write back stage. So now I have the number of the register I want to write to over here. And then when I write back, when I'm in the write back stage, I'm going to take this value and I'm going to bring it back and I'm going to provide it as the write register number. So the write register number is going to correspond to the write register of the instruction that's in the write back stage, not the instruction that's in the decode stage. Is that clear now? Okay, great. Okay, so now we have our pipeline data path. When we talk about pipeline, there are two diagrams that we like to use. The first is the multi-cycle pipeline diagram, and I've been using this diagram a lot so far. So now I'm going to modify this diagram a bit to show where the pipeline registers are. Okay, so this is the pipeline. This is the diagram that we've been using before to show how instructions execute in the pipeline. So now all I'm showing is how we have in between these different stages we have these pipeline registers, and also in this diagram what we're doing is we're coloring the parts that are used. So for example, the data memory here is used in the load word instruction, but it's not used in the sub and the add instruction. Okay. So this here is a multi-cycle. This here is called the multi-cycle pipeline diagram, and I've been using this diagram a lot throughout the past lecture. But there's another diagram that we also like to use when we reason about pipelining and when we analyze pipelines, and that's a single cycle pipeline diagram. So what does a single cycle pipeline diagram do? Well, it gives us a snapshot at a single cycle. So for example, if I wanted to know what was going on in the pipeline at cycle 5, then what I can do is I can draw the pipeline, the different stages of the pipeline, with what instruction is at each stage. So here we know that the add instruction is going to be in the instruction fetch stage. Here it's IM because it's saying instruction memory. So here we're labeling the resource, not the name of the stage. Okay. Here the load word is going to be in the instruction decode stage. Add is going to be in the execute stage. Sub is going to be in the data memory stage, and then load word is going to be in the write back stage. So here, the way I can show this is by showing the pipeline diagram that we had before, and up here we write the instruction that is inside of each stage. And here you'll notice that the earliest instruction is the instruction in the last stage, right? So here the load came before the sub instruction, and that's why the load is ahead of the sub instruction in the pipeline. Okay, so whenever we say a single cycle pipeline diagram, this is what we refer to. We refer to this pipeline with also all the different instructions drawn over their corresponding stage. Okay, is it clear what I mean by this? Okay, great. So with that, there's one more topic for today, and that is the control signals. So far I've been drawing these control signals as kind of standalone things that are floating in the middle of the air. But the question is, where do the control signals come from? Where do we get the control signals from? Where did they come before? Okay, so obviously we use the opcode to derive the control signals. Okay, we use the opcode to derive the control signals. and we use the func field for the ALU controller. So here the ALU controller takes the func field and it takes the ALU op control signal. So we use the opcode to get the control signals, but who gets us the control signals from the opcode? So the control unit is going to be responsible for extracting the control signals from the output. So where in this pipeline do I put my control unit? Right, we should do it instruction decode, exactly. So we always want to do things as early as possible in the pipeline. Okay, so since instruction decode only depends on the opcode and the opcode's available to me here, what we will do is we're gonna put the control unit in the instruction decode stage as early as possible, and this way, by the end of the instruction decode stage, I have all the control signals for my instruction. So now that I have my control unit, what do I do with the control signals that I get? Do I just connect them to all these different locations? So just take all these control signals and connect them to my control unit. Can I do that? Right. I can't just take, for example, ALU source and connect it to the control unit. I can't just up here connect it to the control unit. Why not? I can't take here branch connect it to my control unit. Why can't I do that? So the reason I can't just take ALU source and connect it directly to my control unit is because the ALU source here corresponds to the instruction that is in the execute stage. But the control unit here is giving me the ALU source for the instruction that's in the instruction decode stage, right? Similarly, over here, the mem write and the mem read, these are for the instruction that's in the memory stage, right? But the control unit is going to be giving me the mem write and the mem read for the instruction that's in the instruction decode stage. So I can't simply take all these signals and connect them directly to the controller. What do I need to do? Right, I need to pass them through the pipeline, exactly. So what we're gonna do is we're going to also pass the control signals through the pipeline. So when the control unit decodes the opcode and figures out the control signals, it's gonna pass them to the pipeline register. Okay, I'm gonna have a set of control signals for the execute stage, a set of control signals for the memory stage, and a set of control signals for the write-back stage. And then over here, when I get to the execute stage, I'm going to pass the control signals. So here, when I get to the execute stage, I'm going to get the control signals from the pipeline register. I'm going to provide them to ALU source, ALU op, and regdes. Okay? And then when I get to the memory stage, I'm going to get my control signals from the memory control signal, the M control signals, and I'm going to pass these to the branch, mem write, and mem read. Okay? And similarly, when I get to the write back stage, I'm going to get my control signal from the pipeline register. I'm going to pass it to mem to reg. Okay? So there's one more control signal. What about reg write over here? Where do I get reg write from? Do I get it from this control unit? Where does reg write come from? What does reg write do? Correct, exactly. So reg write is going to come from the write back stage, exactly. So reg write tells us whether or not we want to write to the register file on this cycle, right? So which stage is responsible for writing to the register file on this cycle. It's the writeback stage. Okay, so the writeback stage, so we're going to get reg-write from the control signals of the writeback stage. Okay, just like we got the register destination, the write register from the register number of the writeback stage, and just like we've got the write data from the data in the writeback stage, we're also going to get the reg-write control signal from the control signals of the writeback stage. Okay, so this is how it's going to look like. We're going to have ALU source, ALU up. We're going to have the control signals for execute, memory, and write back propagating through the pipeline. We're going to get the control signals for execute from here, and then we're going to get the control signals from MWrite from here, and then we're going to get the control signals for writing back from here. And most notably, reg-write is going to come here from the write back stage. So every instruction is going to figure out all its control signals in the instruction decode stage, and then it's going to take its control signals with it to every stage so that it uses them in the right stage. Okay, any questions about this? So this is our pipeline data path. Now we are correctly handling the control signals. We're correctly handling the write back. We're still not handling data hazards and control hazards. We will handle those. We will look at how to handle those in upcoming lectures next week. Aside from hazards, this is our pipeline data path. Any questions?
Professor, till what lecture is included in the exam?
So the exam is in 2 weeks. So next week's material at the beginning of the week will be included. So you have 2 more lectures for the. Okay, so those lectures will basically cover how to support, how to handle hazards in the data path. Okay, so they won't be kind of a major new topic. You've already looked at data hazards. You've already looked at the pipeline data path. So we have 2 more lectures where we'll be seeing simply how to modify this data path to support handling hazards. Okay, other questions?
Sir, I have a question. It's somehow irrelevant to today's topic, but to the data path in general.
Yeah, go ahead.
For the branch for the I format instructions, like branch equal load word, they are the offset at the constant is always positive, right? And we want to have to branch
it could be negative, because if you're branching backwards, right? If you have a do while loop, you would have to branch backwards. So branch it could be negative, yes. Also, if you have a load instruction, you could have a negative offset.
Okay. Thank you.
So it's possible for you to have a negative value here in the offset, and in which case that's why you need sign extension. Also, the add immediate instruction, it can take a negative immediate value, right? That's how you subtract a constant.
Yes. But for the ALU, it's ALU is either signed or unsigned, right? We depend on the ALU for this.
So the ALU control unit will tell our ALU if we're doing a signed or an unsigned value, because you have an add and an add unsigned instruction, right? You have 2 separate instructions.
Yes.
Based on the opcode and the funct field, the ALU controller will be able to tell if it's doing a signed or an unsigned addition.
Okay.
And it will tell the ALU accordingly. So if you're doing a signed addition, the ALU will treat the inputs as 2's complement values. If we're doing an unsigned addition, the ALU will just treat them as positive numbers.
Oh, much clearer. Okay, thanks.
Okay, yeah, you're welcome. Right, any other questions? Okay, well, if questions, you can read more about what we covered today in section 4.6 of the textbook, and that is all for today, and I will see you next time. Bye, everyone.